Okay, so continuing on with this example, we've come up with a description of the set E, the solid that we want to integrate over as a set, and we're going to use this to set up our integral. So our triple integral that we want to evaluate over the solid E, integrand is z dv. We're going to start by using our definition to write this as the double integral over d of, and then here is the first variable. First variable I'm going to integrate with respect to x, and these are going to be the limits 0 to y over 3. My integrand is still z, but again integrating with respect to x here, so dx. And then I have a dA out here. And we'll deal with the double integral and this dA after we've dealt with what's going on in here first. So this is going to look like the double integral over d of, now integrating this with respect to x, it's going to come out to xz. Okay, and the limits again, there's 0, y over 3, dA. I know that we're plugging things in for x here, because that's the variable I integrated with respect to. If I plug a 0 in, whole thing goes to 0, so it's really just y over 3. This will become yz over 3, but I'm going to pull that 1/3 out to simplify the notation a bit. D yz dA. All right, now this time, because the whole thing has been reduced down to a double integral, I can use any technique I want for evaluating this double integral. And as you should recall from the previous video, we described that region D in terms of polar coordinates. So I'm going to try and evaluate this using polar coordinates instead of rectangular. That means we need to rewrite this as 1/3. I found my limits of integration for polar down there. 0 to pi over 2, that's for my theta. 0 to 3, that's for my r. And then remember, I can go back up here again. We have these conversion formulas for polar coordinates. We're working in y's and z's instead of x's and y's. So that means my y is going to become r cosine of theta. My z is going to become r sine of theta. And then remember, dA becomes r dr d theta. Okay, this is a gigantic product, and I can separate out the functions of theta and the functions of r respectively. So this is going to become 1/3 times, this will be cosine of theta, sine of theta, d theta, and again my limits are 0 to pi over 2. Integral, there's r, and r, that's going to become r cubed dr from 0 to 3. Now this integral you can handle in a couple of different ways. I can use a u substitution where u is sine of theta, then cosine of theta d theta would be my du. Alternatively, the approach I like to use is to use a double angle formula for the sine function to convert this. Cosine theta times sine of theta would equal 1/2 sine of 2 theta. And if I were to pull that 1/2 out and multiply it to that 1/3, this will turn into 1/6 times the integral from 0 to pi over 2 sine of 2 theta d theta. And then again I have this integral here that I haven't done anything with yet. Now let's evaluate all of this. So this is going to leave me with 1/6 times the integral here is going to become -1/2. So it's just, I'll put the negative in right there. -1/2 cosine of 2 theta from 0 to pi over 2. This becomes r to the 4th over 4 from 0 to 3. At this stage, it's really just a bunch of evaluating, plugging things in, and working them out. I'm going to leave that part to you. All of this, once everything's been plugged in and simplified down, becomes 27/8. All right, and that's it. So did want to point this out. I'm being very intentional in the way that I'm writing out my set E here. I'm not looking for bounds on x, y, and z necessarily, the way I did in the previous example. And the reason I'm doing that is because I know that this region D is going to be represented in polar coordinates, not rectangular coordinates. If I went through the trouble of finding bounds for y and z respectively, it wouldn't really matter because I'm not going to use those bounds directly. Instead, I'm going to be converting everything into polar. So that's my rationale behind using this notation here. Let's go ahead and move on to another problem. Okay. So this time what I want to do is take an integral. Notice the integrand is not actually given to us explicitly. It's just written as f of x, y, z. And that's because we're not actually performing any of these integrals. We're just doing setups. We want to rewrite this integral in 6 different ways where E is the solid bounded by this cylinder in the planes x equals -2 and x equals +2. So the idea here is to note that there's 3 different types of solids we've discussed, type 1, type 2, and type 3. And for each one of those solids, once we project them into one of the coordinate planes, the plane region that remains can be either a type 1 region or a type 2 region. So that gives us a total of 6 different possibilities for the setup of our integral in any one of these problems. And because we're given a description of this solid, we would want to start with that and then try to interpret it as all 6 of those different types of cases separately. So y squared plus z squared equals 9. I believe we actually dealt with that exact cylinder in a previous example. In fact, the very last example that we did. So let's draw this out. Z, y, and x. So we already know this is going to look like a cylinder which has a radius of 3 centered at the origin. So looking at the circle in the yz plane first, I'm going to have 3, 3, -3, -3 there. So we're going to have a circle like this. And then the cylinder is going to go kind of along the x-axis like this, but the planes x equal -2 and x equal +2 are going to cut this cylinder, cut it off. So I'm going to attempt to draw that. This never looks that great, but that's all right. Here I'm going to have a few points. I'm not being super careful about my drawing. I probably should be, but yeah, that's pretty terrible. So it's all right. Hopefully that gives you a general idea. So we have a cylinder that's sort of going along the x-axis, centered at the x-axis. Even though my solid looks pretty bad, it's okay because we're going to be paying more attention to the projections of the solid into each of the coordinate planes, and that's going to be a lot easier to draw. So because each of those type 1, type 2, and type 3 solids each project our solid into a different coordinate plane, I want to consider all 3 coordinate planes and what the projection would look like. The projection onto the YZ plane is the easiest one because we kind of already drew that. YZ, so that's Z and that's Y. If I project this solid onto the YZ plane, it's just that circle centered at the origin, radius 3. So we have this. Okay. That's what I would be thinking of as my region D. If I projected this region onto a different plane, let's say the XY plane. Okay, we'll take a look at the XY plane because the cylinder is on its side, if we projected, I just realized I covered up the entire page by doing that. If we projected this onto the XY plane, then what you're going to get is a rectangle where the interval on the x-axis is -2 to +2. Interval on the y-axis is -3 to +3. So that's pretty easy to sketch. If this goes from -3 to 3, this goes from -2 to 2. I get this rectangle right here. And that's what I'd be calling D in that case. I get kind of the same general shape if I do the only projection I haven't considered yet, the projection onto the XZ plane. Again, if you look at this poorly drawn cylinder, the XZ plane, the plane that kind of goes into the page, if I project onto that, we're projecting from this direction. It's going to also create this rectangular projection. You can even think of it as the cross section of that cylinder with the XZ plane in this case. It's a rectangle. And again, on my x-axis, the interval is -2 to 2. On the z, my interval is -3 to +3. So we get essentially the same looking rectangle. -3 to 3, -2 to 2. Okay, so now that we've done that, what we want to do is come up with the different setups for our integrals. So what I'm going to do, normally I would write out, D equals, and then this is a set, D equals, this is a set, D equals, this is a set. And even though I could still do that, it ends up being kind of a lot of writing. And you're going to find in some cases it's just a little bit easier to just go from the picture. So let's think about the different types of regions that we're looking at here. In this case, I'm projecting this solid into the YZ plane. X is the only variable that's not accounted for here. That would make the X the variable that I want to deal with on my inner integral. The Y and the Z are going to be accounted for on my outer integrals. So let's think about what that looks like. So let's do this. Starting with the inner integral, f of x, y, z. Like I said, for this first case here, we're going to have a dx on the inside. Now looking at the solid, x only varies on the interval from -2 to +2. So that's going to be what I use here, -2 to +2. Okay. Excuse me. So now having written that, I want to look at how y and z are dependent on each other. So for example, if I want to integrate with respect to y, I have to think of y as dependent on z. Now notice, I can think of this right half of this semicircle as the equation y equals the square root of 9 minus z squared. Similarly, I can write here y equals negative square root of 9 minus z squared. It's the two halves, the right and left half of this circle. Those, I shouldn't have done that so close to this. Those are going to give me bounds on the y. Y has to lie between these two functions. So that's going to mean that my y lies between negative 9 minus z squared, negative square root of 9 minus z squared, and positive 9 minus z squared under a square root. Finally, I have to integrate with respect to my z. Well, z, remember this outer integral has to have constants, and z goes from -3 to +3. So those are going to be the limits on my z. And this got all kind of muddled up in here. But hopefully that makes sense what I did there. Okay. All right, now if I wanted to rearrange some stuff in this initial case, my x still has to be the inner integral. So I'm still looking at this f of x, y, z dx as the inner integral from -2 to +2. And this time I want to switch up the order of integration here. I'd like to do dz here and dy last. Now, even though I switched the order of integration here, it's not a simple matter of just juggling these two integrals. I can't just switch these two. And the reason for that is you can't have the outer integral with limits of integration that look like functions like this. Remember, they have to be constants. So I have to rethink how I put restrictions on this region. Rather than think of this as a right and left half of a circle, let's think of it as a top and bottom half of a circle to put restrictions on z. Z is going to have a lower bound of negative square root of 9 minus y squared, and an upper bound of positive z equals positive 9 minus y squared. So that's going to be what the limits of integration look like here. Negative 9 minus y squared, positive 9 minus y squared, both under square roots. Finally, what do I have on my y? My y goes from -3 to +3, so those are going to be the limits that I use there. Okay, and I'm running out of time on this video. I'll do the last 4 versions of this in the next one.